Reaching these autonomous tiers requires abandoning the legacy pipeline in favor of a specific 7-phase AI-native lifecycle blueprint. Phase 1 replaces requirement gathering with pure data analysis. AI ingests massive user logs and competitive benchmarks to spot patterns in user friction. The output is a product requirement document embedded with feasibility scores, ensuring the scope is grounded in data before engineering begins. Phase 2 is data architecture. Modern software engineering requires a strict, continuous synthesis of execution logic and underlying data structures. Autonomous agents take over the tedious work of cleaning data streams, pre-processing inputs, and generating synthetic data for edge case testing. Automated personally identifiable information detection must be integrated into this architecture to guarantee privacy by design. In an AI-native ecosystem, this data ingestion pipeline acts as the application's true nervous system, often superseding the raw application code in importance. If the solution requires specialized AI, Phase 3 involves selecting the right brain for the task, whether that is a transformer, a specialized CNN, or a specialized LLM, all constrained by hardware limits. This MLOps scatterplot illustrates the trade-offs. Tracking hyperparameter tuning through frameworks like MLflow or weights and biases is mandatory to objectively evaluate model performance. The primary engineering decision here is weighing the cost efficiency and latency of a small, fine-tuned model against the broad capabilities of a massive, general-purpose LLM. Phase 4, Agentic Implementation, splits the workload. The human acts as the skeleton, strictly defining system boundaries, constraints, and API schemas. The AI acts as the muscle. Multiple parallel agents flood these defined boundaries, instantly generating code, unit tests, and documentation. Implementation speed is no longer gated by how fast a developer can type. It is gated by how precisely the human can define the guardrails for parallel agentic orchestration. This new exponential execution speed inevitably creates a catastrophic failure point when we reach Phase 5, the verification bottleneck. When agents generate code at 10 times the human rate, traditional code review fails at scale. The output inevitably clogs the CI/CD pipeline. This verification matrix is the architectural fix, an LLM as a judge framework. Tools like RAGAS or TrueLens evaluate AI outputs autonomously. These driven test suites simulate thousands of complex edge cases instantly, running scenarios a human tester might never conceive. Without automated LLM evaluation, a high-velocity AI workflow collapses under the weight of its unverified output. Phase 6, Intelligent DevOps, involves the dynamic release of both software logic and model weights. Predictive maintenance utilizes AI to monitor the CI/CD pipeline in real time, identifying anomalies and predicting which builds are likely to fail before they even finish compiling. Finally, Phase 7 introduces continuous stewardship, replacing the traditional concept of reactive software maintenance. This line graph shows the system continuously monitoring for data drift, detecting when incoming data deviates from the training baseline. When performance drops, it responds autonomously, triggering self-healing and retraining loops to restore peak efficiency without human intervention. The AI-native lifecycle never truly ends. It is a permanent, self-optimizing loop governed by dynamic data, not static code.